Precalc honors limits day 4, limits involving infinity. Previously, we discussed the limits of rational functions with the indeterminate form 0 over 0. Now we will consider rational functions where the denominator has a limit of 0, but the numerator does not. As a result, the function outgrows all positive or negative bounds. If the value of a function gets larger and larger without bound, we say that the limit has a value of positive infinity. And if the value of the function gets smaller and smaller without bound, we say that the limit has a value of negative infinity. So let's take a look at this rational function y equals 1 over x. Now we've learned in previous chapters that since we have this x in the denominator, we have a vertical asymptote at x equals 0. Right there. Okay, so if I'm looking at the limit as x approaches 0 from the left of f of x, this is going decreasing without bound, so it's going down to negative infinity. Limit as x approaches 0 from the right of f of x, well, now that's increasing as we approach 0 from the right. So that's going to positive infinity. Now, since our left and right hand limits are not the same, we're going to write that the limit as x approaches 0 doesn't exist. Okay, now let's think about when our x values are approaching infinity. As our x approaches infinity of f of x, this function approaches 0. It's getting closer and closer to 0. Same thing when it approaches negative infinity. And that we learned, that's the same as our horizontal asymptote rules. Looking at that function, you could see that the bottom's bigger. So we could say our bottom dominates. Then your horizontal asymptote is y equals 0. Remember 0 like J-Lo. The next function, when limit as x approaches 0 from the left, of f of x is going up towards infinity. Limit as x approaches 0 from the right of f of x also is going to infinity. So our limit as x approaches 0 of f of x, we could say is infinity. That's our most, that's the most descriptive that we could be. Technically, infinity does not exist. Remember, we went over that because you can't actually reach a value of infinity. So just keep that in mind. All right, then the limit as x approaches infinity of f of x. Looks like we're approaching 0 again. Limit as x approaches negative infinity of f of x. Also looks like it's approaching 0. So that's how you would look at these graphically. Let's take a look at if we have to do these algebraically. We already talked about vertical asymptotes. So the next example, sketch a graph, label the vertical asymptotes. Okay, so a couple things I know about this. I'm looking at my denominator, and I know that I have a vertical asymptote at x equals 3, because that's what's going to make my denominator undefined. The other thing I know is that I have a horizontal asymptote at y equals 0, because our bottom dominates. The degree of the denominator was greater than the degree of the numerator. Okay, so let's sketch a little graph here. All right, right, drawing my vertical asymptote, that's at x equals 3. Horizontal at y equals 0. And you can make like a quick table of values of this if you want. I'm just going to draw this in to save time. I'm going to show you that this looks like this. So you would just like pick a few points, put in the values, put it into the original function and see what it gives you. All right, so the limits as x approaches negative infinity of f of x, looks like we're approaching 0 right over here. Limit as x approaches infinity of f of x, so looking over to my right, also looks like it's approaching 0. Limit as x approaches 3 from the left of f of x, decreasing without bound, so that's going to negative infinity. Limit as x approaches 3 from the right of f of x, also negative infinity, decreasing without bound. As we learned about an indeterminate form 0 over 0 in vertical asymptotes, there's also other indeterminate forms. We went over that a couple lessons ago. So you can have 1 to the infinity, infinity minus infinity, infinity over infinity, or 1 over infinity. And that's, if you get that algebraically, you're going to have to think about the end behavior of the function in the horizontal asymptotes. Okay, so this graph we kind of already did. Limit as x approaches negative infinity is 0. As it approaches infinity is 0. And we know that we have that horizontal asymptote at y equals 0. So horizontal asymptotes and end behavior limits, these are all linked together. So you actually know a lot already without even knowing that you know a lot about this with limits. Okay, so we're going to call these limits at infinity, and the line y equals L is the horizontal asymptote. Okay, so just again, looking graphically, we got a horizontal asymptote at y equals 1. So limit as x approaches positive infinity, we're approaching that horizontal asymptote as 1. That's our end behavior is approaching that. Same thing, the left hand side to negative infinity. Okay, so now we're going to look at these functions and decide what we're approaching. Your limit as x approaches x squared. Now, if you were to plug in infinity, that would be infinity squared, which would just lead you to like a larger infinity. The other thing you could do when you're thinking about these functions is like make yourself a little sketch. X squared looks like a parabola, and positive infinity going to the right, it's increasing without bound. It's going up to positive infinity. Okay, now here again, if we plug in infinity in both the numerator and denominator, you're going to get infinity over infinity, but that's not actually your answer. What you want to do is think about your horizontal asymptote. So our horizontal asymptote rules say that if the degree is the same in the numerator and denominator, then we're going to take those coefficients. So our horizontal asymptote is going to be y equals 3/6, which is 1/2. So our limit as x approaches infinity, positive infinity, of 3x plus 5 over 6x plus 7 equals 1/2, because that function, you know, there's 1/2 on your graph. There'd be a vertical asymptote somewhere over here, is going to, you know, kind of be like this. So you're actually approaching that horizontal asymptote 1/2 instead of infinity over infinity. So that would be an indeterminate form. Think about it, the horizontal asymptote rules. Okay, for this one, now if I'm thinking about the limit as x approaches infinity, so let's say you took the square root of this, we're going to get square root of 2x if we just look at that part, and we can, the 5 is a little bit insignificant, so we're going to just not worry about that for now. Minus x. Radical 2x is a bigger number. So if you're plugging in infinity, you're going to get a bigger infinity minus infinity, which is still going to lead you to infinity. But then, let me show you an example. If you have limit as x approaches positive infinity of radical x squared minus 5 minus x, well, now if I kind of think about how that simplifies, let's go pink. This would simplify right here. That would just be x. Again, the 5 is kind of insignificant. Minus x. So now we're doing infinity minus infinity. That's actually going to give us an answer of 0. So not all infinities are the same. So yeah, again, looking at this, if you plug in infinity, infinity to the third is going to give you infinity, infinity squared is going to give you infinity. But if you think about this function, this could simplify to be limit as x approaches infinity. Simplify x cubed over x squared, you get x. I know there's going to be a hole at x equals 0 because those x's canceled out. My end behavior, this is a line. So it starts down, ends up. It's an odd function too, so we know it starts down, ends up. It's a line with a hole in it. So if I'm going to infinity, my answer to this is going to be infinity. If you were asked the limit as x approaches negative infinity of this function, well, it simplifies to be x. As we're going to negative infinity, well, that's decreasing, so it would be negative infinity. Okay, so here's our 3 rules, and they're the same as the horizontal asymptote rules. So good refresher from the beginning of the year. If the highest power of x appears in the denominator, so if it's bottom heavy, like J-Lo, it's going to approach 0. So in each of these, let's look at our coefficients. X to the 6 is bigger than x cubed, so it's going to approach 0. Over here, we got an x squared is our highest degree in our numerator. X to the 7th highest degree in the denominator, so approach 0. If the highest power of x appears in the numerator, that's top heavy, so we could say that the top dominates that. Okay, so when that happens, we're either going to go to positive infinity or negative infinity. So what you can do is look at your leading coefficients there. And then kind of simplify it. So this is going to be 5x to the 7th over 2x fourth is just our leading terms. That simplifies to be 5 halves x cubed. And what I'm going to think is, okay, that is a function with an odd degree. The end behavior for a positive odd degree starts down, ends up. So as I'm going to infinity, infinity would be over on the right-hand side, I'm going to approach infinity. Okay, this next example here is the same exact function. But this one's asking you when it approaches negative infinity. So On the left-hand side, going to negative infinity, we're approaching negative infinity. We're going down. Okay, for here, now they tried to make this tricky because the leading is in the middle there, negative 12x to the 15th, 12x to the 3rd. So I'm going to do the same thing. I'm going to go look at those leading and simplify. That's going to be negative x to the 12th. That's 15 there. Negative x to the 12th. Okay, so we have an even negative function. So even negative is going to start down, end down. So as I'm approaching positive infinity on the right-hand side, it's going towards negative infinity. Okay, again, same function. So you'd simplify to negative infinity. You're still decreasing without bound, so it's negative infinity. All right, then the last section, oh no, rule 3, we forgot rule 3. I was gonna move on too quickly. Oh, this one's easy. If you have the degree of the numerator is the same as the degree of the denominator, then you just use your coefficients, just like with the horizontal asymptotes. So degrees are the same right there. That simplifies 15 or 5 over 15. So that equals 3. 1/3 actually. All right, now leading coefficients in this one, we got negative 16x to the 11th, and we got 5x to the 11th. All right, so same degree, we're using these. That would be your horizontal asymptote, so that's what you're going to be approaching, whether you're going to infinity or negative infinity. Okay, now for the limits involving radicals. You have to be really careful with these. You always have to be careful with radicals. But if we think about, where do we go into? Negative infinity. All right, so we got to think about this function. I'm going to look at the leading in both the numerator and denominator. Leading in the numerator is 2x. Leading in the denominator is like a radical x squared. So this is 2x radical x squared. Okay, now if we think about the denominator, since this x is going to be squared, our denominator is always going to be positive, which is good because we want positive for radical. So denominator is always positive, and let's just simplify that a little. We can write that as 2x radical x squared is x. So that simplifies to be negative 2. Now you would think, oh, it's going to be 2, but you're going to negative infinity. So you're plugging in a negative value in your numerator. Your denominator is going to be positive. So that's kind of tricky right there. Okay, let's look at number 1. Practice problems. The limit as x approaches infinity. Okay, so this one, oops, I'll highlight that. Bottom dominates. So we're approaching 0. Number 2, look at the leading coefficients, same degree. So that will be 3/6, which reduces to 1/2. Okay, 3. Looking at my leading terms. Okay, so I got 4x squared. Radical 9x to the 4th would be my leading terms. All right, again, the denominator is always going to be positive. This is not that much of an issue because we're going to positive infinity rather than negative infinity like this example up above that we did. So let's see, this is 4x squared over 3x squared, and that will be 4/3, same degree. Okay, number 4, same degree. Use your leading coefficients. 4/3 again. Limit as x approaches negative infinity. Okay, so let's look at our leading terms. (5x squared over 4x). All right, that's going to reduce to 5/4 x. 5/4 x is a odd positive, starts down, ends up, because that would be to the first power. We're going to negative infinity, so we're looking at the left-hand side. So our answer is going to be negative infinity for that. All right, and the last one. Again, look at our largest degree in our numerator, negative 11 x to the 7th, 6x squared. All right, let's write that out over 6x squared. Okay, so that reduces to negative 11/6 x to the 5th. So that is a odd negative function, a negative odd function. So it's going to start up and down. And we're going to negative infinity. So we're looking at the left-hand side, so that's going to be infinity. Okay, so that's it for that. One thing, I want to go over just right at the end. Maybe we should have gone over earlier in the lesson, but just the end behavior rules. So if you have an even positive function, start up, end up. If you have even negative, you're going to start down, end down. Odd positive, you're going to start down, end up. Odd negative, you're going to start up, end down. Okay, so that's that. Thanks for listening.